Welcome everyone. Let's wait for 5 more minutes to see if other people join. Then we shall start. Okay, so I think we shall start. So welcome everyone. This is NOC139 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudhir Das Gupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So yeah, we are now in our week 7. Okay. So by this time, I think you are well acquainted with this prerequisites so that I do not need to reiterate. So yeah, this is week 7. It was supposed to be on 8th September, but this is how it is. We are doing it today. So this Sunday there will be no session from 3 to 5. So from next week we shall keep our Sunday schedule on. So yeah, let's begin. So the plan for today is to wrap up the CMOS problems and CMOS. So we'll see basic problems on CMOS sizing and how to calculate uh, delays of a chain of gates, and then maybe touch upon a little bit on the analog amplifier large signal analysis of MOSFETs. Okay. Okay. So let's begin. So we are asked to find out the logical effort of a three input NAND gate, right? So how to begin with this kind of problem? First, I need to tell you that what we are looking at. So first, okay. So any CMOS design has two networks. Okay, it will be something like this. So a set of inputs will be applied. So these are inputs, and here you will take the output. Okay, we are discussing about combinational logics today. So this will be your supply rail VDD. This will be your pull-up network. This will be your pull-down network. Okay. So now I want to ask you that what do you mean by CMOS? What is the full form of CMOS, by the way? Full form of CMOS? Anyone? You have been reading this, right? This CMOS amplifiers, CMOS inverter. So what is this CMOS? This is nothing but your complementary MOS. MOS is the same thing, metal oxide semiconductor. So what do you mean by complementary? Is that you have, suppose something you have A, so you will have a complement also in the same system. Okay, so this is your pull up network, this is your pull down network. Okay, by the way, why do we call the upper one pull up network and the lower one pull down network? Do you want to comment? By the way, what is the simplest CMOS circuit? You know that it is inverter, right? So we have been told that this will be how my inverter should look like. Let's say this, I can short it or write it in this form. And then this is my F. F is the output and this is VDD, right? So here, let's say this is my pull-up network and this one is my pull down network. Okay. So by the way, why do we call it pull up and pull down? I think it should be obvious by now. Do any one of you want to comment? You can unmute and speak up. Means what the network is pulling up or what the network is pulling down.
One is charging and other is discharging.
Fine. So you mean to say that there is, let's say, capacitance here, load capacitance. So what? So let's say my this voltage corresponding to is V out. So if the capacitance is charging, so what is getting pulled up? It has to do with pulling up of something, right? So what is being pulled up? You are absolutely right. It is related to charging and discharging. But you need to tell me specifically what it is pulling up. Just think a little bit. It should be obvious. It is pulling up the V out, right? Charging means what? Your capacitor voltage, node voltage is getting higher from 0 to VDD. That means you are pulling up the voltage. So that is why the top half of the CMOS logics are called pull up network because it pull ups the output to a value of 1. Okay. Similarly, when your this discharging path is on, then it is basically pulling down the V out, or in another word, this is making F to 1, this is making F to 0. That means you are emptying the tank or the capacitor. Okay, you are discharging the capacitor. So this is how the nomenclature came about, the pull up network and pull down network. So one thing you have noticed that in CMOS inverters, we have always kept PMOS in the pull up network and NMOS in the pull down network. Okay. Another thing, just let me point it out at this point. At an at any time, one of PDN or PUN will conduct. Okay. So this is important point to remember. So now the question is why PMOS is used in pull up network and why NMOS is used in pull down network. So I want you to answer me this question. This should be understood very clearly, right? So what are the purposes of this thing? So let's say we take two cases. So let's say I have my pull up network. So pull up network means what? This node will be connected to CL. This is my VDD, and let's say this is NMOS. Okay, and similarly this is my CL, this is my PMOS. And also assume that initially my voltage is 0. Okay, because ultimately the purpose of pull up network is to pull up the voltage. So I can pull it up from any value. So let us, for digital, as we are discussing the digital circuits at this moment, so we'll just assume that the it is pulling up from a value of 0. So now tell me what should be the gate voltages if I want to have the pull-up network conducting. For NMOS case, for the pull-up network to be conducting, I should be applying here VDD, right? Or on. And I should apply ground or 0 voltage in case of PMOS, because when I am applying 0 volt at the gate, then my PMOS gets turned on, and we will see how. So this is the gate terminal, this is the source terminal, this is the drain terminal, right? Similarly, can you tell me what is the, let's say this is gate terminal, and what about the other terminals in case of PMOS? What is the terminal? What is this terminal? Is it drain or source? So this is your source, right? In case of PMOS, my source is connected to the higher potential, and this is your drain. Fine. Now think that this is basically your charging path, right? This thing should charge. Now in case of PMOS, till what value my CL will be charged? CL will be charged from 0 to VDD, right? Why? Because when CL will be VDD, then there is no difference between the source and drain potential of the PMOS, so current will not flow, or only your leakage currents will flow. So moral of the story is that when PMOS is used in a pull-up network, this voltage, this voltage always is greater than your VTP, or the threshold voltage, right? So, so what? So your PMOS will always be turned on, and your CL will be charged from 0 voltage to entire way till VDD. Okay. But in case of NMOS, what is happening? Note that the important voltage in this case is this one, gate to source. My gate to source voltage should be greater than threshold voltage for the NMOS to be on. That means as soon as my CL is charged up to VDD minus VTN, beyond that my transistor will be off. Do you see? So your VGS is changing here. VGS is basically VDD minus V out, right? This node voltage is your V out. So my VGS should be greater than equal to threshold voltage, for that matter my NMOS to be on. So that is why in this case I am getting a signal swing at the output 0 to VDD minus VTN, where in this case I was getting full swing. In this case I was getting a reduced swing. Okay, so this is not preferred. Why? Because you want, this is your 0 volt, this is your VDD, right? So when you draw your inverter, if you keep your PMOS, what was the region? This was your VTC, right? Something like this. So it will just not be entirely at your VDD. So when you define, let's say this region as your 1, so your noise margin starts to reduce. Okay. If you have gone through the lectures, you know about the noise margins. So your noise margin starts to reduce. So that is not a good thing. You cannot distinguish your, due to presence of noise, you cannot distinguish your level of signal as 1 or 0 clearly. Okay, so that is why for a pull-up network your PMOS is used. So this is better, and this is not used generally. Same thing is happening in case of pull-down network also. So in case of pull-down network, what is happening? Let's say this is your CL, right? And this is your, let's say, NMOS. Similarly, we'll show a parallel case of with PMOS. This is CL, this is your PMOS. So again, my pull down network is in place. That means my pull down network has to be active, and that means that my NMOS has to be on and PMOS has to be off. Then both of the path are conducting, and that means this is discharging through this MOSFET, and this capacitor is discharging through this MOSFET. Let's assume that earlier it was initially it was charged to VDD, okay, and we want to see till what point it will get discharged. So again we see the same thing, we will understand the same way, that this is my gate, this is source, this is drain in case of NMOS. In case of PMOS, this is gate, this is source, this is drain. Fine. So my gate to source voltage is always fixed and my transistor will always be on. So that means this transistor will always conduct, and that means V out has a swing of, will get discharged from VDD to 0, the entire range. But in case of PMOS, what is happening? The important voltage is this one, VGS, or in other words, VSG. So my VSG is what? In case of PMOS, V out minus 0. So, and my V out is changing, right? So, as soon as my V out is VTP or less than that, so V out is basically discharging. So, level of voltage at the V out will drop. So, it will, as soon as it drops below the threshold voltage of the PMOS, my transistor will be off. So there will be no path. That means my capacitor will not get discharged further. So that translates to V out changing from VDD to modulus of VTP, because VTP is negative. Fine. So you see again the same thing. Lower half of your noise margin is getting compromised. Okay. So this is basically what is happening. In this case, you are getting full swing. So it is preferred. And it is not preferred because reduced V out swing. Okay, so this is the reason why we use PMOS in the pull up networks and NMOS in the pull down networks. Okay, is that fine? So concluding is that NMOS are always used in pull down network, and PMOS are always used in pull up networks. Okay, so these things you should understand why this is so in case of CMOS logic. So now what we will do, we'll try to build some larger gates. Gates mean logic gates. So what are the universal gates, by the way? Can any one of you unmute and tell me what are the universal gates? So your NAND NOR, these two gates are called universal gates. Why? Because from these gates you can construct the fundamental gates, okay? Fundamental set of gates, and or and invert or the NOT gate. So this you will do as homework, that why your NAND and NOR are called universal gates. Okay. So now looking at how to, so moral of the story is, if we can make NAND NOR using CMOS logic, we can get any higher order logics. Okay. So our target is to make NAND and NOR using CMOS logic. How will you do that? Very simple stuff. First, let us look at the pull down network, or let's say this is your CL and this is your F or V out. Fine. So this is A and this is B. So can you tell me what kind of logic will this provide? This is 0 0 0 1 1 0 1 1. Okay. Please tell me what will be the F column. Anyone? Take case by case. What in case of 0 0? In case of 0 0, what will happen? This will be off. This will be off. So this will retain its previous value. So it will retain its previous value. Fine. And what about 0 1? This is off. This is on. That means what? It gets a path to discharge. So output will be 0. Fine. Similarly, 1 0. This will be on. This will be off. Again a path to discharge. So this will be 0. And if both are on, then it gets two paths to discharge. Fine. It is more suitable. Then it will also be 0. Fine. Similarly, what about this? One zero one one. So in case of 0 0, both transistor will be off. So it will hold previous state. as it is in series, so any transistor if off, it will hold the previous state. And if both the transistors are on, or in the case of 1 1, then what will happen? It will get the path to discharge. So your output will become 0, or your capacitor CL will get discharged. Okay. So now, as it is a pull down network, if you assume these previous states to be 1, so what kind of logic you are getting? What is the truth table of this logic? Can I write F as this? Can I write this?
Yes, sir.
And what about this
A dot B bar, NAND gate.
NAND gate, right? So now still we have a ambiguity about this one, this previous states. We are not sure, we are not for sure know that previous state will be 1. Okay. So let us see how my pull up network behaves. So again, if you see your pull up network, so this we have been discussing PDN topologies. Okay. Now if you see your PUN topologies, so PUN is made of PMOS. So let's say two PMOS circuits are in parallel. In this case, this will be my output and this will be VDD. So this is A, this is B. So your A, B and F 0 0 0 1 1 0 1 1. So what is the case of F? When 0 0 means both transistors are on. In case of PMOS, what? 0 0 means, in case of PMOS, 0 means transistor is on, right? So this is on, this is on. So there will be a path through which my output capacitance will get charged. That means my output will be simply 1. Fine. Similarly, when any of the transistor is on, my output will be 1. And if both the transistor is 1, then what? This is also not connected, this is also not connected. So F will hold its own state. That means previous state. So this again, if you see the truth table of this represent to this one. So F will be your, this contraption gives you the NAND operation. Okay. Similarly, if you just connect two PMOS circuits and this is your CL, let's say this is your F, this is A, this is B, this is your VDD. So A, B and F 0 0 0 0 gives you both transistor are on. That means this gives you 1. 0 1 means A is on, B is off because this is PMOS. So there will be no connection because these are connected in series. So again, this will be previous state, this will be previous state, and this will also be previous state. So previous state, if we assume 0, then we see that this contraption give us the OR operation. Okay. Now to build the CMOS logic, what we need to do? What was our structure? This was our VDD. This was our pull-up network. This was our pull-down network. And this is our F. And here we have the multiple inputs. Okay. So similarly, let's say I want to construct two input NAND gate, and in parallelly I will also construct two input NOR gate. Okay. So what was my PUN for NAND? This was my PUN for NAND, right? So this is VDD, and these are my inputs. And now I want to construct my PDN. PDN for NAND was this one. So let's say this is A, this is B, and this will be my output F. Okay. So now if you see, let's say, let us mark that this is M1, M2, M3, M4. Okay. So if I now want to check A, B, F, okay, and let's say I want to check M1, M2, M3, M4, F. So what will happen? This is 0, 0, 1, 1, 0, 1, 1. These are the all possible combinations you can give. So when A is 0, what is the A is 0 and B is 0? What is the status of PMOS? M1 is on, M2 is on, M3 is off, M4 is off, right? So your output is 1 because your this PDN, so this is now your PUN and this is your PDN. So basically what is happening, your conduction is or your active path is your PDN only, right? Sorry, your PUN is only active in this case, in this combination. Your PDN is not active because 0, 0 at the input will make my NMOSes off. Similarly, in this case, what is happening? 0, 1, 0, 1 means M1 will be on and your M2 will be off. Similarly, your M3 will be off and M4 will be on. Fine. So what is happening? This is on, this is off, this is off, this is on. So what do you think? Your PDN is on or off? Does your PDN conduct? It will not conduct, right? Because one path
Series
is, sorry,
not conduct because that is in series.
that is in series.
Both
Exactly.
should be one.
So output will be, your output will be what? Only PUN, only your PUN is conducting. That means output it will lift up, pull up the output. Output will be 1.
Yes.
So in this case, your PUN is conducting. Similar case is in this case also, just your this thing will reverse. Okay. And what about this? When both the transistors are on, in that case,
Zero
you
grounded.
you have M1 off, M2 off, but your M3 and M4 on. Fine. Then your PDN is conducting. Then your PDN is conducting, and what does it lead to? It leads to pulling down the output to 0, right? Now you can cross check that if it is your NAND truth table or not. Okay. So this gives you the operation of NAND. Okay. Similarly, from the previous discussion, if you connect your pull-up network and pull-down network in this fashion, so this is your pull-up network, this will be your pull-down network. You just do the similar kind of analysis, assuming a load capacitance here, which is getting charged and discharged. You can easily see that this type of contraption is giving you OR operation. Okay. So far, is it clear?
Yes, sir.
Okay. Now coming back to the sizing of these transistors. Okay. So now what I expect that you take any combinational logic and design the CMOS equivalent. So what do you need to do? If you remember, if your digital electronics course, you need to make it in a product of sum or sum of product kind of combination. Then you can easily break down your expression into NAND or NOR implementation. Once you are aware of how your NAND and NOR implementation are there, then it is simply boiling down to knowing about these things. Okay. So this you please practice. This thing is very important. You can take any standard textbook and start solving the exercises. Okay. Now coming back to the point of sizing. So how to, let us take the example of NAND, two input NAND. How to size a two input NAND gate. So what was our implementation? Our implementation was something like this. This is VDD. Here I get my output. This is A, B. This is A, B. Okay. So what did we understood in our inverter course last week? So this is our inverter basically, right? This is A, this is A, this is F, this is VDD, this is ground. So from now on, I want to visualize the inverter in a sense that this is my pull-up network and this is my pull-down network. Okay. So what was the delay associated with it? We found out that TP is equal to TPLH plus TPHL divided by 2. And to have symmetric TPHL equals to TPLH, what do we need to have? We need to have R on of P MOSFET is equal to R on of N MOSFET. Okay. So this we have seen because your TPLH low to high is what? 0.69 times CL times, that is R of what? P MOSFET or N MOSFET? You should be able to answer this by now. What is the subscript should I write? P MOSFET or N MOSFET? On resistance of what? You can easily see, right? This is low to high transition of the output. This point I have explicitly mentioned in last class that LH refers to low to high transition of the output. So low to high transition means what? Pulling up, right? Pulling up the output. That means top network. That means PMOS. So this is R on of P and this is R on of N. Fine. Do you remember? So to have these two same, I need to have R on of P equal to R on of N. Now I want to read it as R for a larger circuit. I will have multiple combination of PMOSs in the pull-up network and multiple combination of NMOS in the pull-down network. So read it as R equivalent PUN is equal to R equivalent of PDN. Okay. So this is the condition which will lead us to sizing of the CMOS inverters. Okay. Now if I give you that, by the way, how do we note annotate the size of the transistors? What do this means? This is 3, let's say this is 6. What do this mean? This means your W by L ratio. Okay. So this is how we denote the sizes. So now the question is mobility of hole, let's say 1 over n times of mobility of electron. Let's say 1 over k times of mobility of electron. K is generally your 2 to 3. So how about my R equivalent? R equivalent of PUN should be equal to K times of R equivalent of PDN if W by L of PDN and PUN are same. Fine. Other way to say this is if my mu P is equal to 1 over K times mu N, so my WP by WP by LP has to be K times WN by LN to have R equivalent of PUN equals to R equivalent of PDN. Please tell me if you understand this statement or not. In last session, I had derived the expression of R on or R equivalent and showed you that it depends on the inverse product term of mu times W of L, W over L. So to have this R1 equals to R2, we need to have mu n times W by L, Wn by Ln should be equal to mu p times Wp by Lp. Right? So as my mobility is reduced, so my width of the PMOS has to be doubled or increased by k times. Is that okay?
Yes, sir.
So if you are given that mobility of electron is k times of mobility of p, can I write this size as 1 and this size as k?
Yes, sir.
Okay. So if that much is clear to you, so now let's assume k equals to 2 because this is the most practical case. Okay. So now can you tell me what is the, okay, before that, let us draw the switch equivalent model of the same circuit. So this is your R on, let's say not R, let's say on, you understand, right? It should be on resistance only when it is on. So this is Rn, this is Rp, this is Rp, and this is my VDD. So this is A, this is B, this is A, this is B. And this is my pull up network, and this is my pull down network. So this is basically your pull up network, and this is your pull down network. Okay. So now understand one thing. What is the worst case resistance in case of pull up network? Worst case resistance. What is that for pull up network and what is that for pull down network?
RP for pull-up network and 2RN for pull-down network.
Why do you say so? It is correct. First of all, why do you say so?
Uh, for pull-up network, anyone should on, then zero should be pull-up,
Right. And
and
what about if both are on? Then what will be my resistance?
R by 2, RP by 2.
Rp by 2. So that is, we
Link.
cannot we cannot take into account that one case, right? We need to take into account the worst possible case. Fine.
Yes, sir.
So similarly, in case of pull down network, it is twice of Rn. Okay. So now can you tell me to have R equivalent of pull up network equal to R equivalent of pull down network? This is our condition, right? Which we want to meet for symmetric delay. So what should be my value of Rn? Let's say
RP by 2.
Rn should be Rp by 2, right?
Yes, sir.
Let's say Rp is equal to R, some fundamental unit. So my Rn should be R by 2, right? So can I say if Rn to be Rp by 2, can I say that my Rn, this individual transistor size, let me do it in here. So you see, by default, you know that this will be 2, right? This 2 is from where it is coming? This is coming from the value of k equals to 2. And now my entire pull down network should be having a resistance of 1. should be having a size of 1, right?
Yes, sir.
So if I make these two transistor double sized, then my resistance will get half, and the series combination will give me a area something like 1. Do you get this point, or I will explain in detail? So this basically what is happening, this twice size is giving you the resistance of R by 2. This is giving you the resistance of R by 2, and this is giving you the resistance of R. If you do not take into account this K value, right? If you take into account this K value also, then it is also giving you R by 2. Or let me just tell it more clearly, that the on resistance of this transistor R on is inversely proportional to your W by L, okay, times mu. By default, as my mobility of PMOS transistor is half of that of mobility of NMOS transistor, I have to make my size of PMOS transistor twice bigger, okay, that is for sure. So suppose I had two MOSFETs above and one N MOSFET, so I would simply make the size of this is 1. But in case of my this two input NAND gate, I have another MOSFET, NMOS, right? So that adds the resistance in series. So thus I need to make the size twice, because the signal here in the discharge path has to travel through the entire set of resistances, this resistance also and this resistance also, in the worst case scenario, or in the only case scenario when it will conduct. In other case it will just not conduct. When both are on, then only it will conduct for this two input NAND gate. So when they are conducting, think about the delay. What was the delay then? Your TP high to low would be 2 times, or 0.69 times from this plot, 0.69 times CL, here is your CL, times Rn plus Rn. Okay, now you want to make this equal to your TPLH, that is your 0.69 times CL times Rp. Okay, so this is why the size of this transistor has to be made twice. Similarly, for example, you can easily tell me, what about the NAND gate? Sorry, what about the NOR gate? This is A, this is B, this is A, this is B, this is VDD, this is your F. So first thing, what should be your approach? Your approach is, let us look at the pull down network. So pull down network, worst case, one path will be conducting. So I can simply make it size 1, and now I want to compute the size of PMOS or the pull up network. So So pull up network size should be what? Size should be twice. This size should be twice. Now again it is in series, two series combination. So I have to just simply make it further bigger, right? So do you see the sizing of NOR gate? Is it clear to you?
Yes, sir.
If it is clear to you, then if we go back to the question that three input NAND gate, okay, and it is given that mu n is 3 times of mu p. So let me just draw the gate first. So this will be your pull up network and this is your pull down network. A, B, C. This is your F. This is your A. This is your B. This is your C. This is your VDD. So please tell me how to size this. If you have understood this and this, you should be able to tell me based upon this condition what should be the sizing.
Same sizing.
No, no. Tell me the value.
111.
111 in case of what?
Uh, in case of NMOS,
NMOS 111.
yes.
Okay. And in case of PMOS?
Again 1 because 3 times, but in parallel, the 3 by 3 is equal to 1.
So what is the series resistance in this case? If you make it 111,
Okay. Sorry, sir. 3, 3, 3.
it should be 333, right? And what about the PMOS sizing? So again, what should be the approach? Approach should be that first identify the pull down network. Okay. Identify the pull down network, identify the worst and make it one. Okay. And identify the worst case. Worst case is when this is also on, this is also on, this is also on, right? So series resistance inversely proportional to your size. So this should be 3 times because 3 elements are in series. Fine. Now if this is 1, so this should be how to size your PUN. PUN should be sized based upon this, right? How, what is the difference of your mobility? So PUN should be 3 times, and worst case is when one path is conducting. So everyone should be 3. So identify PDN, size overall 1, make sure to identify worst case resistance to size each elements in the path. PUN sizing will be determined by mu n equals to k times mu p ratio. Identify worst case path in PUN and size them accordingly. Okay, so this should be your strategy whenever you find out any such kind of CMOS logic sizing problem. Okay, now tell me one thing. With this, what should be the inverter sizing? This is A, this is A, this is F, this is VDD. So what should be the sizing here and what should be the sizing here with this? Anyone?
1 and 3.
So it will be 1 and it will be 3, right?
Yes, sir.
So now can you tell me what is the input capacitances? What is the input capacitance? C input of inverter. Let's say your one unit of gate capacitance is Cg. So it will be what? 4 times Cg, 3 Cg in parallel with 1 Cg. So it will be 4 times Cg because Cg will scale with area, right? So your W is increasing, W by L is increasing.
Yes, sir.
So this is your 3 Cg, this is your Cg, okay? So now can you tell me what is the C input of 2 input NAND? Sorry, 3 input NAND, or let's say in general, let's call it logic. So what is the capacitances here? 3 Cg, here 3 Cg, here also 3 Cg, here also 3 Cg, 3 Cg, 3 Cg. So what is the input capacitance C in logic? Anyone? To get this thing, you need to first understand that we are talking about only one input with respect to one input, okay? Because these two will be shorted and connected to only one pin. So then what is the input capacitance in this case for any particular input? It is simple, right? In the similar fashion, it is 3 Cg plus 3 Cg. 3 Cg contributed from PUN network and 3 Cg is contributed from PDN network. So it will be 6 times your Cg. Is that clear, by the way?
Sir, you said sorted. What is sorted? All three sorted.
No, no, all three not shorted. Shorted means, suppose, okay, just let me show you. Means when you fabricate your NAND gate, right? So you will have this kind of connection, let's say this, then you have these three things. So how will you connect this outside the, let's say this is one IC you have. So you will have one pin here for output F, and let's say you have three pins here. One is A, one is B, one is C. So this A will be connected to what? It will be connected to this, and it will be internally shorted to this and connected to this. Similarly, your B will be connected to this, and internally it will be connected to this. Similarly, your C will be connected to this, and one connection will go to this. So what you get in your hand is that this box, okay? You do not know anything inside. It will be just marked as 3 input NAND, and it will be marked as this is your pin 1, this is your pin 2, this is your pin 3, this is your pin 4, which is your output pin. Okay, you do not get to see what is inside. So now if you see that you have a capacitance here and you have a capacitance here. So what these two capacitances are in parallel because these
Yes.
nodes are in the same position. So this is what? This is your 3CG, this is your 3CG. So what is your C input with respect to A input 1? So if you can translate it to simply like there is a 6CG capacitance, okay? Drawing this and this, that's the same thing. Do you see?
Yes, sir.
So basically that is why your C in logic is 6CG and C in inverter is 4CG. So your logical effort is defined as C in logic divided by C in inverter. Remember that this inverter and logic are based upon the same mobility scaling law, mobility ratio rather. Okay, so this mobility ratio is important. So this inverter also have to be designed with the same mobility ratio. This inverter has to be designed with the same mobility ratio as that of this logic. That is why I have explicitly drawn this. Otherwise, I would have just put 1 and 2, which is more conventional, right? But that is not how logical effort is defined. Assuming the same mobility ratio, what is the input ratio of input capacitances of the logic with respect to inverter? That is your logical effort. So this is what your 6CG over 4CG, that is what 3 over 2. Okay. So for a 3 input NAND gate, 3 over 2 is the logical effort for. Okay. Now quickly can you tell what is the logical effort for this case? So what is C in logic here? C in logic I can see 4CG, and C in inverter is what? C in, if you draw an inverter with the mobility ratio of 1:2, so you will get what? You will get 2 and 1. So you will get 3CG. So what is your logical effort? 4 over 3. Okay. So don't assume that logical effort for 3 input NAND gate and 2 input NAND gate will be the same. Logical effort varies depending upon the number of input. Why does it do so? Because your number of inputs will determine this ratio, that how much is getting connected in the series path, and that will also dictate the sizing of that path, right? That dictates the sizing of this path. the worst case path, and thus that dictates the sizing of your capacitances also, and thus that dictates the logical effort value. Okay, so now if you are given any combinational logic, will you be able to calculate the logical effort? Still not confident?
Yes, sir.
So you try some problems, okay, with various kind of combinational logics, so you will be able to calculate this kind of stuffs. But understanding the basics is very important. Okay, so let's move on. By the way, do you know about clock gating? Means try to answer this question. Basically, what is the power dissipation we discussed in last class? P dynamic plus P static mostly, right? But P static is much less than your P dynamic. Okay, so most important component of power dissipation in a CMOS logic is your dynamic power. Do you remember the formula of P dynamic we derived in the last class? Anyone? CL VDD square times P 0 to 1 probability of 0 to 1 transition by the clock and clock frequency. This we have discussed in detail in the last session. So one of the way to reduce the dynamic power is by reducing your F clock or the clock frequency. If you reduce your F clock, then your P dynamic reduces. But what do you think? Reducing P clock is a good option? Should we reduce F clock? I want to know your opinion on this. Obviously, from power point of view, it is absolutely yes. But what about speed point of view? By the way, what does your clock frequency determine? If you have studied synchronous logics in your digital circuits course or digital electronics course in your undergrad or second year BTech, so you must have seen that your clock frequencies, you must have seen that rising edge or falling edge or level clocking, right? You remember these things?
Yes, sir.
So these things determine when your instruction is getting carried out or your circuit is getting operated. Okay. So you see, when you increase your speed point of view, it is a big no. Because the most struggle in today's industry, why we have gone to multiple cores in our processors, is that we cannot increase the clock frequency beyond around, let's say, 5 gigahertz. That is the state of the art. Okay. AMD
Yes.
processors, that is the state of the art, 5 gigahertz. 5 gigahertz, huge power consumption. We can easily go to 10 gigahertz, but then what will happen? Your chip will melt instantaneously. Not a single operation will be carried out. Okay. So from speed point of view, reducing the clock frequency is not a good idea. So how to get away with these things? The way to get away with this thing is use the clock only when instructions are carried out or circuits are in operation. Okay. If it is not in operation, remove the clock. Okay. So how do we do that? A simple way is that, let's say I give you a, by the way, what is this gate?
And a OR gate.
This is an OR gate. Okay. So let's say this is your clock signal and you feed some kind of control signal which indicates you that it is time that you shut down the clock or turn on the clock. It will be something like step function, step signal. So the output of this is your gated clock. Okay. So what is happening basically, let's say this is your clock signal. This is your clock signal. Now let's say your control signal is something like this. So let's say this. Okay. So this is operation phase. This is idle phase. Okay. So how will your gated clock look like? Your gated clock will look like, in operation phase, it will simply operate, and then as soon as it gets, it doesn't switch anymore. Okay. The clock becomes idle. So now can you tell me, if this is let's say signal 1 and it is signal 2, so obviously you can see that P01 times F clock is lesser in case of signal 2 because my clock is not switching. So this is called your gated clock. Okay. This is used why? To reduce effective F clock, thus reducing your dynamic power. So reducing dynamic power consumption, it is being used. Okay. So you may ask that why this is not correct, decreasing the clock frequency. So if you read the definition of the frequency at this point is different, frequency at this point is different, though this is an absolutely periodic signal. So you cannot define your frequency in that sense. So you cannot explicitly say that you are reducing your clock frequency. What you are reducing is basically your effective product of these two terms. Okay. And mostly in the modern synchronized circuits, you used rising edge or falling edge kind of triggering. We call it triggering. Remember, edge triggering, level triggering.
Yes, sir.
So in this case, in this idle phase, what will happen? It will not get any edge. So simply your operations will not be carried out. Okay. So this
Yes.
is what is clock gating and this is why it is used. So yeah, now moving on to the next problem. Calculate the delay for the, so they want us to calculate this D for the two input NAND gate. Means I am putting some signal here. So what time does it take to come to this? Okay. Drives two input NAND, 10 two inputs NAND gates in the given below. Mobility is this, this is this. Okay, fine. So two input NAND gate, we have some information that we know what is the logical effort of two input NAND gate of two input NAND gate with mu n equals to 2 mu p. We know that it is 4 over 3, right? Okay, so let us keep that in mind. So what is the delay of an inverter? By the way, that this we derived in our last session, right? Let's say this is CL. So this is my input. So I will have it on this here, and I will have a this here and this here. So this will be my 2CD. This will be CD. This will be 2CG. This will be CG. So what is the TP or time delay or propagation delay? We found it to be 0.69 times R equivalent times CL plus 3CD. This we called what? C internal. You remember this formula?
Yes, sir.
So what was going on there? This is this R equivalent. We were multiplying it with C input. And what was my C input? C input was 3CG and C internal was 3CD, right? Times CL plus CL by C in plus C internal by C in times C in times this we are calling as F and this we are calling as gamma, right? This formula we know, right? So F was what? F was electrical fan out and gamma was self loading. Fine. So now what do we do? We take this R equivalent into, let's say, we take our gamma outside. R equivalent C in times gamma times 1 plus F over gamma. This you can write. So by the way, what is my C in times gamma? C in times gamma is nothing but my C internal. C internal 1 plus F by gamma. So this we call it as a TD or unit time delay. I will tell you what is this. What does this actually mean? Unit delay. Okay. So what about my formula now? My formula becomes TD times 1 plus F over gamma. Fine. Okay. This is the case of inverter. Now, what is TD? TD is basically, so this circuit is same as this circuit, right? So this was my CL and this was my C in and this was my C internal. Fine. Now TD is your delay of the unloaded inverter. What do I mean by that? I mean that let me take this inverter. This is C in, this is C internal. So what is the delay? What is delay of this circuit? What is the propagation delay of this circuit? This is nothing but 0.69 times R equivalent times C internal only, right? Because there is no load capacitance, it is unloaded. This is what we are defining as TD. So do you understand what this TD is or the unit delay is? So I will not move until you tell me that you understand this much. Okay? Because this is very
Yes.
important.
Yes, sir.
So you got this much, right? So next we
Yes.
can move on to NAND gate analysis. Okay. Let's move on to two input NAND gate analysis. Delay of a two input NAND. Assuming mu n is equal to 2 mu p. Okay. So first let us draw the circuit. This is A, this is B, this is A, this is B, this is F, this is VDD. So what about the sizing? Can you quickly tell me what is the sizing? How should we approach? First, look at the pull down network. So entire pull down network, we do 1. Fine. Then we see the critical path and break down that and we see that two resistances are in series. So we make it twice. And pull up network is determined by the mu n by mu p ratio. So that is why it pull up network should be 2. Now we see the critical path. Critical path is only one resistance. So we simply write it 2. Okay. So this is how you size it instantaneously. So now the question is, how do I compute the delay of this circuit? So let us look at the capacitances. This has 2Cg. This has 2Cg. Okay. I am concerned only about one input. Okay. Because my one pin I will be looking at to compare with any other values or to compare it with respect to the inverters. You can write that there is also this, but this does not concern me. 2Cg. What about the output? So this is, there will be 2CD, here will be 2CD, this is the drain, there will be 2CD, and here also there will be 2CD. So from this diagram, can you tell me what is C in of logic and what is C internal of logic? C in, obviously we have earlier also seen it is 4Cg, right? But what about this C in logic, C internal logic? This is the node, right? So please see and tell me what is the value of capacitance at this node. 6CD, exactly. It is 6CD, right? So if I draw this as a two input NAND gate, what should be my C internal and what should be my C in? This is my C in logic and this is my C internal logic. Okay. Now, what is the load in this case? For this stage, what is the load? What is my CL? Can you see that CL is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times of C in of the next stage. That means your CL is what? 10 times of your C in logic, because these are also two input NAND gate, right? Same, this resistance, this capacitance will be present at these places also, which will act as the load capacitance for the input NAND gate or the first NAND gate. So do you see this CL is equal to this? Anyone? So this, you got it right?
No, sir.
You did
Sir,
not get it. Yeah.
sir, C load will be resultant of C in and C.
C in and
Uh, sir, there is two capacitor, so
in
that
which
will
place?
in AND gate. Sorry, NAND gate.
In NAND gate, there are two capacitances. One is the internal one, another is the load capacitance.
So the yes, sir.
In case of load capacitance, so basically what is happening, so one NAND gate is connected here, right? And there are 10 other NAND gates. Okay? Let's say these are the 10 NAND gates. So what there is an input capacitance here, that is my C in logic. Similarly, this will also have C in logic. This will also have C in logic. This will also have C in logic. These all capacitances come into parallel. Fine. And also there is an output logic of this. I have an output logic here also, but that does not concern me, right? Because it is driving this capacitance only. Now is your doubt clear?
Sir,
Yeah,
sir, sir, one, one more thing.
yeah, please.
How this?
You can ask in Hindi also if it is comfortable.
No, sir. ठीक.
Is it fine?
Yes, sir.
Okay. So I assume that you have seen, you have finally seen what is happening. So now what we'll do? We'll derive it simply in the same manner. So what was my delay now? Delay is 0.69 times R equivalent times C in logic times, or let's not go into there, just directly write CL plus my C internal. What is my C internal? We'll see. Okay. So now what do I do? R equivalent times C in times CL by C in plus C internal by C in. Okay. In the same way, we'll just take this common C in times C internal over C in, and this will become CL by C in over C internal by C in plus 1. Okay. So now this is 0.69. This is R equivalent. What is my C in? C in is my 4 CG. Okay. 4, or let's not go into that because my C in will get cancelled. C internal is my 6 CD, and this will be 1 plus CL by C in will be CL divided by 4 CG, and this is 6 CD divided by C in. Okay. So now what is my delay unit? This is my 4 CG. Fine. Now this, if I do R equivalent times, if I keep my CD inside and take 6 here, then what will I get? 6 plus, let's call this stuff, this thing, F dash. Okay, so I will have F dash over the 6 CD will get cancelled. So I will get 4CG, right? Just let me simplify the mathematics for you. I think it is getting complicated. So we are here, right? Till this much you have seen. C in, this is C in. Okay. So this one are equivalent times, let's say C in is my 6, C in is my 4CG times 6CD over 4CG, CL by 4CG, 6CD by 4CG plus 1. Okay. Now let's cross this. What is the inverter delay I had? Inverter I had 3CD, right? Remember that inverter, if I draw the same inverter,
Yes, sir. 3 CD.
I had 3CD. So if it is 3CD, then I have 2 multiplication here, and let us call this term a new value f dash. I'll explain this and give you a simplified formula. Okay. So this is f dash over times 4CG over 6CD plus 1. So now if you simplify it further, so you will have this, we call that TD, TD, and let us take 2 inside, 2 plus, now what are we getting? F dash time CG over CD times 4 over 3. Okay, this we can simply write at in generalized term, TP is equal to P plus F dash times gamma times G. So what is your T? TP is your propagation delay of logic. What is your TD? Please tell me what is TD? Propagation delay of unloaded unloaded inverter or delay unit. What is P? P is basically your parasitic factor. And what is P? If you assume it very carefully, P is nothing but your, okay, just I'll define these terms also. F is called your electrical fan out, gamma is your self loading, G is your logical effort. Okay, so this is the final delay formula of your any gate for that matter. In our case, P is 2, G is 4 by 3 for a 2 input NAND gate. Remember that. So now definition of TD is nothing but 0.69 times R equivalent times C internal of inverter or 3D for that matter. P is defined as C internal of logic divided by C internal of inverter. So in 2 input NAND gate, what was the C internal of logic? It was 6CD. And what was C internal of inverter? We know it is 3CD. So it is 2. Okay. And what about F dash? F dash is defined as C load over C in of logic. So what is CL in our case? CL we have found out to be 10 times C in logic. So 10 times C in logic, divide your C in logic, that is equal to 10, and gamma is a technology parameter, that is equal to 1. This also has explanation, but that will require another time. This, if time permits, I will cover this portion in the summary session, which will be week 13. Okay, there will be one additional summary session at the end. I will cover this at that point. Why gamma is equal to 1? It has some physics behind it. And then what is your G? G is defined as, G is logical effort, right? So this is C in of logic divided by C in of inverter. So that is in our case 4 over 3. So now if you need to find out TP, simply plug in this value. P is 2, F dash is 10, this is 1, and this is 4 over 3. So 46 over 3 TD or 15.33 TD. So your propagation delay is 15.33 delay units. So see, there are two ways to go for these problems. Either you remember this formula, okay? This remembering this formula may lead to some wrong answers many times because you won't be able to comprehend what are the values every time. So what I suggest generally is that understand this part very carefully and what these individual terms mean, what this means, what this mean, what this mean. Okay, if you understand these terms very carefully, it will be just a piece of cake for you. These internal terms where we have found out, where we have discussed in these places, what is this, what is this, what is this and this. These 5 things you need to understand by looking at any gate, then you will be easily able to get this formula. Okay, so please do not remember this formula, just see the form, or tactics will be, you understand that TP will be some inverter delay times parasitic plus loading. Okay. So parasitic, how will you find out? This parasitic you find out from this value. C, C internal logic or the drain capacitance at the logic divided by the drain capacitance of the inverter, assuming both are designed with the same mobility ratio. Okay. Similarly, F dash is your electrical fan out. That is what? Load capacitance divided by input capacitance of the logic. Gamma always take 1 until unless specified in the question. And logical effort you can quickly find out, right? You just need to know the structure of the device, structure of the schematic, and how to size them. Okay. So this is the most difficult problem in combinational logic delay analysis which you will face in this course. Okay. So moving on to the next problem. Again the same thing. We want to find out the delay. Fine. First thing we need to understand what should be the sizing. So TP, let's say this is stage 1 TP1, this is TP2, this is TP3. So TP will be TP1 plus TP2 plus TP3. So what is TP1? TP1 you have found out that it is nothing but TD times P plus F dash G and gamma. Okay. Similarly, we'll go for, let's say this is stage 1, this is stage 2, and this is stage 3. So you have given that mu n is equal to twice of mu p. That much you know. But you remember in the inverter chain problem, how we dealt the delay? We dealt the delay by minimizing the overall delay with respect to size of each of the stages, right? And that was done by that this is if your C load and if it is your C in, so C load by C in should be equal to F1 times F2 times F3. That was the F1 was what? C ratios, right? Remember I have solved it using Cj minus 1. So in this case what is given? In this case it is given the first stage, the input capacitance of the first stage is C. That means C in is C and the load capacitance is also C. And this one we have found out that this should all be equal. It's all the F's or the ratio of the sizes should all be equal. So your FQ is equal to 1. So that means your F equal to 1. In other sense, all stages have same size of transistors. Okay. So in that case, I can simply multiply 3 times TD plus TD times P plus F dash G gamma. And for one stage, we know it will be TD. P we know it is 2 for 2 input NAND gate. F dash, what is F dash in my case? Now, F dash is, earlier it was 10 times, earlier it was what? 10, right? Why 10? Because 10 gates were connected in parallel. In the current case, what is connected? Only one single gate is connected. So F dash will be 1. G is G is the logical effort we found out, right? 4 by 3. And gamma is 1. So if you compute this, this will be 3 times TD, and it is 2 plus 4 over 3. So that will be 10 TD. Okay. So 10 delay units. This will be the solution. Now what will happen if your CL by C in, let's say, is equal to 8? Size the transistors and find out delay. Okay. This you try to do it in the homework, and I will discuss this in the summary session. Okay. At the last, week 13. So how will you be able to try this out? This problem, the previous problem, and the inverter chain problem I did in the last session. So those three problems will come into handy. If you understood those three problems very clearly, then you should be able to solve this question. Okay, just try. Okay, if you do not get, don't worry, I'll solve it in the summary session. So given that time, so last question is this: the two-in-tap process CMOS fabrication follows the steps employed. Okay, so what is happening? First you have a substrate, then you dope it, let's say P type, then you do what? Then you oxidize it, then you apply photoresist, then you apply UV light using mask, then you etch this much, then you apply your tubs, right? Then you etch entire stuff. So once this is made, so this is the first step you do. Okay, so NOL formation is the first step you do. Then what you do? Then you do again oxidation. Then again you make the windows. Again you make gates and all. So this becomes your second step. Okay, you make your gate oxide and field oxides. After that, what you do? After that, again you create another mask layer. You again use UV light, use photoresist, same method, etch this much out, then do the source and drain doping. Once source and drain doping is done, then you put the metal contacts and then the vias. Okay, so this is your third step, and this is your last step or fourth step, and at last you do the chemical polishing and all. Okay, so your this is first, 3 should be first, 3, then 1, then 4, then 2. So this is your right answer. Okay, so I have not gone into the details of fabrication. I think in lecture Professor Dasgupta has also touched upon very briefly. So you understand that it is a bottoms up process. Okay, and multiple layers of masking. Photolithography is what? You apply a photoresist, cover some portion with a black mask, cut some window, apply UV light, that photoresist will get dissolved, then etch back the oxide. This same method is going on and on. It is just kind of, Legos you have, if you have played in childhood Legos, then you will see that this is the same way you build story upon story, and then finally again you etch back, finally you create the contacts. Okay, so this is nothing difficult. So we'll stop here. Analog portion will start from the next week. But please, I will request you to revisit this lecture and understand, if you have missed something, understand these two problems very carefully. this one and the first one. Okay, this will help you in general in your GATE exams or also in your interviews for IITs. Okay, so that's all for today. If you do not have anything, let us end the session.